Okay, so let's start with a little more theoretical presentation about the Raspberry Pi Pico guitar effects, or abbreviated Pico effects. First, this is the left side. This is how the device looks like in the first prototype, and one of the key things I've done for the first time in my Tinkerer life is to build a custom PCB and order it and have it printed out. This is the part which is needed in addition to the Raspberry Pi Pico is of course an audio codec and some preamplification and so on. Good, I'll start with a system overview. It's a digital multi-effects unit for guitar, can also be used for harmonica because I'm mainly a harmonica player myself, and of course bass and synths or whatever. Intended use, I built it for a simple amp simulator for live use, for going to jam sessions and so on. It's fully open source. There's a link to a GitHub repo in the description of this video where you can find as well the schematics and of course the software and code needed to run this and build and run this device. Some nitty-gritty tech details: it runs at 48 kHz sampling rate with 16-bit sampling depth, so it's not really high but still quite usable for a guitar effect. It has really low latency. That's common to all the hardware-based digital effects. It uses as a 0.6 millisecond round-trip delay, which is really low, of course, but it's I think also many other hardware effects have this kind of a latency. It has 3 live adjustable parameters using potentiometer, has a mono high impedance input obviously for guitar, and a line out also in mono, because it should be a really simple device. It doesn't use any stereo effects so far. It could do stereo, of course, it also could do stereo input, but I'm not using it. What are the basic effect blocks I implemented? I think probably the most simple one is the delay with a maximum delay time of 1.36 seconds. That's due to the limitation there is the available RAM on the effects chip, and for a Raspberry on the microprocessor for a Raspberry Pi Pico, it has quite a lot of RAM. I can use half of it, more or less, which gives you maximum delay time a bit more than a second. Has a modulated delay for flanger, chorus and vibrato effects, an algorithmic reverb, so-called Schroeder reverb. Then an important block for an amp simulation is also a wave shaper. This allows to distort the shape of a waveform. Amplitude device is base, of course, for various distortion effects and also amp simulation. Then has a 64 tap impulse response filter. It's used for cap simulation. It's so sort of a shortened version of a IR filter. And then of course the standard DSP filter, first order IIR filter, is implemented for EQ or preamp modeling, and second order IR filter, which is mainly used also for cap simulation. I tried to do a bit crusher, failed at some point, but this is one of the effects that really sound funny, so I left it as it is. Gain stage, obviously, I think this is probably the easiest effect, just amplification, and they also tried to implement a dynamic compressor. How an example effects program is built up. The device uses presets or like predefined sequences of these individual blocks, which are called an FX program. It's the one I also show in the sound demo most of the times, the high gain amp model. It has an sort of an amplifier section with a high first order high pass filter and 2 wave shapers, and the high pass filter can be controlled with a cut knob. This is the first one. Gain, second one. Then you just choose along which curve of the wave shaper is taken. This already concludes the amplifier part. The cabinet simulation is just a combination of a second order low pass IIR filter combined with a FIR filter modeled after an impulse response I found freely on the web. And then there's also some spatial effects added, just a simple delay with a delay intensity, which is a combination of, I think, mix and feedback, which just when you turn it up there's more delay, and when you turn it down it's less delay. Alright, and just open the case, so to say, to give an overview of how the internals work of this guitar effect. Of course, we have this custom PCB, which contains this guitar preamp part is just mainly impedance converter and also amplifier. Can be controlled by the input volume to account for different pickup or guitar signal levels. This then goes into a CS4270 audio codec. It's also used in commercial audio interfaces. I think it's quite good quality, but it's rather simple to use and to interface. There's a line out which is controlled by the output volume, which is very, very important for live use, to be able to control the volume yourself. And then there's also, of course, data buses to the microprocessor. There's an I2S implemented using I think it's called programmable input-output system, which basically a PI assembly version of an I2S bus is. And then for configuration, there's I2C, which is needed it makes the link between the audio codec and the microprocessor board. Then it also has UI components, a little monochrome OLED display, which is accessed using SPI, and then of course 2 push buttons and the rotary encoder, which is used to navigate within the menu, the little menu it has, and also 3 potentiometers, which are interfaced, of course, using the ADCs from the Pico. And just get more into the IT or more into the programming tech stuff. It leverages the dual core capability of the RP2040, and this allows me to use a 64 finite impulse response filter without any. The RP2040 doesn't have any DSP extension or whatsoever, but it can still do this, which I think is quite amazing. Core 0 does main audio processing, which is all handled using interrupt request routines, and it handles the hardware UI element, so it's just it's basically, if you will, it's kind of an operating system which runs on Core 0, which does the main part of the operating system, and Core 1 is an additional processor which handles the display updates, does some UI processing, and when needed does a finite impulse response calculation, which does it in pretty high synchronization with Core 1, so it effectively, for the FIR, it more or less doubles the clock speed, so to say. What interrupts do we have? Audio buffers, of course. They're just there's a little audio buffer of 16 samples, which is filled using direct memory access. Then we have the rotary encoder increment, which generates an interrupt when you press a button, and of course when the FIR calculation needs to be made, and also obviously for the ADC readouts. Software side, I used the bare metal approach mainly for educational purposes, because at some point when I decided on building such things, I had the interest in learning to understand how a microprocessor really works. What I didn't like doing, or found is really boring, is just typing register definitions. I took this from the CMSys files, and some float math routines honestly were very simply too complex for me to do them so I just took them from the RP2040 SDK. It's written mostly in C, of course, and some critical routines such as startup code and specific hardware functions are written in assembly. For example, the RP2040 also features a hardware divider, which I think just to make full use of it, then assembly is better to really control each clock cycle, so to say. It's based on the makefile, compilable on Linux, and the standard ARM GCC tool chain. Of course, since it involved quite a bit of modeling, also not just programming, but also really shape things. There's some additional Python scripts for filter design and cap modeling, which, for example, divides a recorded impulse response and tries to derive an IAR filter parameter from it, and so on. And there's also a tool for processing wave files through these programs. This allows to develop effect programs without having to upload it at each increment to the actual hardware. That's already it. I think 10 minutes have passed. There's also a sound demonstration video. It's also linked, and a non-talk-through version of this presentation, if you like, which contains some more sound demo.